Good thing is for such common materials, this is the one that starts with alumina, as you can see, so it's a very big database. Of course, you will always find material which is not in there. So in our case, I just look for aluminium oxide, corundum, for example. Yeah, there it is. I double click, and now I have automatically filled these parameters. Yes.
For the YouTube purpose,
yes,
you need to use.
Okay. But I'm not starting from scratch, I guess. We're seeing. All right. So let me get that done. This is now a very, very critical thing, and I have to remind me if I forget it at any point on the next unit. Or the next group of people. So we were lucky here that this was in the database, or also we can find this in literature. You have to be very careful. I know a couple of manufacturers, and I've come across this a couple of times. They tell the customer that they can determine the refractive index. And that, sorry, but that cannot be true. We have an additional software in this package. It's called MeSearch. What you can do is you can make a measurement, you can upload it into the MeSearch, and you can enter certain ranges for these parameters. So the MeSearch will go through each and every parameter, for example, 2,000 iterations, calculate the result for each, and then see where the error, the measurement error, is a minimum. So this can give you an idea where the true parameters might be. But if anybody tells you they can determine, sorry, they are lying. Go on the internet, go to refractiveindex.info, see all the different universities in the world about refractive index. It's not that you just determine that like this. All the scientists in the world, you find different data depending on how you achieve it, theoretically, experimentally, and also this differs. So claiming you can determine it with a laser diffraction instrument just like that, sorry, no, you can't. And I think you have to be that honest to tell a person who's using this, you can approximate it. You can find a value that might work for your material, and then you can use that value, but you cannot determine that. That is absolutely not true. In that case, okay, we have our parameters, so we click Start. We can now enter a name for our measurement. In this case, let's call it F500. That is basically the name of this material. And now the instrument will start working. Pump is on. We set it to pump speed of 40. You hear the ultrasonic going on. First thing that is done is an alignment. So actually the detector I showed you is on a motor, which can be moved in the right direction to always have our main laser spot in the perfect position. So now we're doing a dark measurement. You see no light, no signals on our detector elements. Next thing, background. Laser is switched on now. You see the main laser beam. You see on the first element we always have a little bit of signal. It's just impossible to get this absolutely dark because it's too close to the main laser beam. That's why we do the background, so we can deduct it. And we're already in our sample dilution menu. So at this point we can add the sample, and many questions were how much do I have to add? Well, for the F500 this should be enough. I had the discussion with one person here in the break where I said, yeah, usually you do this by feel, and it's not like you have to experiment with one sample for days. You just start adding a little, and you'll see here, this is the beam obscuration. This shows you, I talked about 10 to 20%, so I think I hit a pretty good spot here. So you just add a little bit, and you see if it's an unknown sample, do I have to add more, or where does it go? Even if you add too much, you can still dilute the dispersion with more water. So actually there are options. It's not like you have to hit and try for a day for each sample. So this is something you'll figure out rather quickly. So this is the first measurement that's done. We had a presetting of 10 seconds per measurement here. Second measurement already running. I mentioned that we do 3 consecutive to verify the stability of our dispersion and our measurement process. So the third one is already on the way. And as I said, I have to stand by as we're improvising here with manual filling. There we go. So of course, now I have also not the exact same filling height as before. If you work in the automatic way, you can set this in the SOP. You tell him exactly in percentage what filling height you want, because that way you make for the next measurement, if you measure the next sample, you have the same volume. You know, we have to add the same amount of sample, which is, when you do it manually, not so easy to hit the right spot. But anyhow, I think it doesn't make a big difference with the things we are measuring here. So we should have 3 curves. Let's check it as a chart. Looks pretty nice to me. So actually we see just one, but that is for the simple fact that they are so much alike. So they really cover up one another, and we see that here on the chart display. We can also check the values. Here we have the D50, which is exactly 17.5 micrometers, and that looks really good to me. So just to give you an idea, there is, of course, a norm for these kind of instruments. The laser diffraction norm by the ISO is the ISO 13320, which states, we did only 3 measurements. In the ISO, you need to do 5. Anyhow, also, it talks about NIST traceable standards. This is not NIST traceable. But still, the limits in the ISO norm here are not higher than 2%, not higher than 1.5, and not higher than 2.5. So as you can see, we are way, 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 way below that. We are even below 0.1 for each of these values, 0.1%, when the upper limit would be the lowest one, 1.5%. So absolutely a good measurement, very, very nice. I'm very satisfied with that. Of course, we will also measure other things, because it would be a little bit unfair just to measure something that we've measured 120,000 times, and we absolutely know what the outcome is, and we know how it works. And as I said, this is also a very, very easy sample. We will now work our way a little bit further to more difficult samples, and to also show you some of the challenges you might encounter when using such an instrument. So, but we'll take it slow. So I'd say the next step, let's measure something a little smaller, like coconut cream. Well, we have 15 minutes, you say, per group.
20 minutes.
Okay, you keep an eye on the, when did we start?
No, 10 minutes already. 10 minutes already.
So another 10 minutes. Okay, then let's try to be quick. So we do the coconut milk, just to have, because this is basically a mix of an emulsion and a dispersion, because in coconut milk you'll have fat, but you'll also have particles. It's actually a very special biological sample. So let's see how that goes. Ultrasonic, I think on that one we can leave it switched off. I will also measure now with Fraunhofer, as I have no idea for the particles. By the way, if you measure an emulsion, the good thing is, for an emulsion you can make a simplification. An emulsion, no matter what it is, you always use the same parameters, 1.475 and 1. That's pretty nice if you measure emulsions, because you can always use the same parameter no matter what. So same process, first of all alignment. I can then the dark measurement, I can already, well, that's a very, very fine pipette you brought me there. Here sampling can be an issue. I mean, emulsions are usually stable, but this, as I said, it contains particle. You can be pretty sure that when you take this from the shelf in the supermarket, there will be a lot of particles sedimented. So if I take it from the top, it could be very different than taking it from the bottom of the, oh, that was a lot, you see. So, wait, let me find a way to put this. That's why you should shake it before use. If you take a pipette from the top or a pipette from the bottom, the result can be vastly different. There you see now I put too much of the coconut milk. So usually I would use the dilute button, which you see in the software right there, and then he will automatically dilute the dispersion. In this case, I can just manually add some water. And now let's have a look at the result for this coconut milk. If we had more time, of course, what we could do is check some sampling issues. Take it from the bottom, take it from the top, compare the results without shaking, of course. Pretty sure you'll see a different curve for the two. next thing that we're going to do, because I think we can do the rest in the end if we have time. So I want to do now something which will be very interesting. Yes?
Can we use our nanoparticles to try this?
What size do they have? Let's do this at the end, maybe. At the end, when we are finished with all the groups, and then you can come back, and then we can do that. Okay? So. We have some carbon black here. Let me maybe take, which one was the already opened one? So I could now just give this, as I did with the 500, directly in the dispersion unit. I will not, because I have experience with carbon black and I know what's going to happen. The reason you usually do what I do now is when you have an unknown sample, a sample you've never measured, I don't recommend you to directly give it in there, because it might be a waste not only of material but also of time. So the standard process when encountering a completely new or unknown sample is always the same. Basically, you first take some water, which is the water? This one, okay. So you put water in a beaker. Oops, who closed that? My wife would immediately say no, that I did that, but in this case it's not true. So let's put some, you know what? Actually, let's keep it open. That's much easier. Hope it actually is water. So you take a beaker with water, and then you take your sample material. The simple reason you do that first is you want to see how does it behave in water. So in this case, and the reason why I used it, you see what the carbon black does? It does absolutely not want to disperse. It completely stays on top of the water. You see a little bit drips in, but most of the stuff stays on top, and it absolutely does not want to disperse in the water. So this is a good example now. If I would put it directly, I would have very little beam obscuration. It would all be swimming on top, and then maybe over time during the measurement more and more drops, so I have an unstable dispersion. And that's not something I want. So in these cases, and that's what we talked about, you need a surfactant, a dispersant. As I mentioned, this is very, very, very strong. But we are on limited time scale here, so I will do something that you normally don't do. You dilute this, a drop on 20 milliliters of water. Of this solution, you can then add a couple of drops in your dispersion. In order to get my point through, I will now take a way too big amount of the dusacine. I will add it pure, but please pay close attention to this layer of carbon black we have on the surface of our water. As soon as dusacine touches the water, you see what happens? It breaks the surface tension of our water, and now with a little bit of steering, we actually can disperse this material. So this is just one example where you would actually need some kind of additive, some kind of tenside or surfactant to add into the dispersion. There's though a downside. So there's a reason why I say dilute this, 1 drop in 20 ml. Because what will a surfactant do? It will create foam. So it's the same as a soap. So it will become very foamy. And what can happen then if we have too much and it becomes too foamy? Foam is basically an air bubble. So it can happen that air bubbles are sucked into the instrument, and as I mentioned in the very beginning, the instrument doesn't lie. It will tell you what it sees. If an air bubble goes through the cell, the air bubble diffracts light just as a particle would. So he will also show you the size of the air bubbles. Pretty sure you're not interested in the size of air bubbles. But that is something, and I added a lot, so it might be we encounter this problem. Let's try. So let's now make another measurement real quick. And call that, we leave all the carbon black. Now I check the amount of material we have in here. could use the pipette, but it's already occupied. I'll just pour it in very, very carefully, directly. So usually you would work a little bit more diligently with sample adding, but we're limited in equipment, we're limited in time, so we just do things the way they come. Let me see, it's also something to prove myself whether I have a good feel for. There you see now the air bubbles. You see the foamy, that it becomes a little foamy from the Dusezin. So then it's very important also to manage your pump speed. If you go with too high a pump speed, the higher pump speed, the more air bubbles you're probably creating. So in these cases, you have to be a little bit careful. It gives you a benefit, the surfactant, but it also gives you some disadvantages, which you have to monitor. So 2 more seconds, and then we're ready to go. I'll get, somebody filled that up, that's good. So of course you don't have to do 3 consecutive measurements, you can do 2, you can do 5, that's up to you. What I often have, in order to find out whether ultrasonic has an effect on my sample, I make myself an SOP where I have no ultrasonic in the beginning, then I make 2 consecutive measurements, then I switch the ultrasonic on, then I make another 2 consecutive measurements. So that way I see the first 2 show me without ultrasonic, is it stable, is it not stable? And then I see with ultrasonic, is there a shift compared to no ultrasonic, and is there a shift during an ultrasonic treatment? So this can actually give you a lot of information about the behavior of your sample material. So carbon black, you want to do a little bit more thorough cleaning, as this is something that really sticks, and you see you don't want to get that on your clothes because it will make black stains immediately. Let's get rid of the first. Did we actually watch the coconut results? We did not watch the coconut results. So let's first consecutive measurements as well, pretty stable. It's about 8 micrometers in the D50, so 2 micrometers on the D10. I'm pretty sure that the fat content is here, and the most of this stuff is solids, which we measure. I'm not an expert in coconut, but it would be my idea when seeing this. Now let's check the carbon black. Actually worked nicely. So would have also been good to show you a bad measurement, that we measure some air bubbles, because the typical size of an air bubble is around 200 microns. So whenever we would measure something like this and then get an additional peak here at 200 microns, you should always pay attention. Could be air bubbles. Could also be material that is where agglomerates are around that size. So this is always something you need to find out. But air bubbles will probably not be destroyed by ultrasonic, while particles or agglomerates will be. So that is a way to find out what of the two it is. Anyhow, this is also a very beautiful measurement we have here. Reproducibility, wow, is actually really, really good for a natural sample. A little bit strange, it's really in the direction of the F500. If you check that, you see. That's a coincidence, by the way. So this was no means planned. You see, I have 3 batches of carbon black. I just picked one, and I didn't know that this would come out in a very similar particle size range as the F500. Once you have your results in, of course, what you can quickly do is go to the print button and select any kind of report which you find appropriate. You can also edit these reports in the software to make it, the way you want it, but this would be a standard one, so it's directly a PDF which you can save, and you have all the information which you need on that page. And as I said, you can really, really change and edit the reports in any way you want. So for anybody who's good with IT, that's a good opportunity to really customize this. So this is the most basic one, but at the end of the day, I got my measurement in 3 seconds. I got my PDF, which I can save, which I can send. So I think that's the most important things that you can do. So have we more time, or we need to shift? We have more time?
No, 20 minutes already.
So then we go over to the next one. Anyhow, officially we finish at 3, but for me it's no problem. If you have your material, bring it here. We'll take a look at it. We'll just try. So thank you very much. And
Okay, we will continue with the second group.
Sapi, do you have a water for me, maybe? A water, yeah. Yeah, mine is empty. Mine is empty. It's empty. Yeah.
Okay, you can also ask your question while workshop.
Thank you. Yeah, thank you very much. So, 55 is what we look at.
My sample. You have already sampled.
I have a couple of samples, yeah. You can. I just said to the other group, if you want, after 3, when we're done with the presentation, with the workshop, you can bring your samples. Because this can take some time. It could be, what is it, calcium carbonate or?
Silicon nanoparticle.
It could be that we waste the entire 20 minutes to just find a good way of dispersing. And so we will do that after 3 if you want. We can just check. So, again, I start with the hardware. Basically, what you see is the way it comes when it's delivered. In our case, we also have the ultrasonic box. This is the silver box right here, which is just attached, you see, to the wet dispersion unit. If you don't need ultrasonic, you can also just leave it out of the cycle and just use the wet dispersion unit. Apart from that, you see monitor, computer, mouse, keyboard, everything comes plug and play, so the software is pre-installed, and that way you can just connect everything and you're ready to go. Also, we have this accessory suitcase coming with some tools for connecting water. Normally, you would have water connected here, so from the tap.
Jadi kita kurang dekat ya Mbak Maiknya. Nggak dengar suaranya.
Karena suara yang
Iya yang di belakang berisik ini.
the other is too loud, so you cannot hear.
Maybe tell them to, because I don't want to be too loud, because then they on the mic it's too loud, you know. So usually you would connect tap water here, which will enable you to have everything automated. You just start a measurement, you can leave, it will measure automatically, it will clean automatically, and once you're back, you have it ready to go. Since we have no water connection, no tap here, we will do a little bit of improvisation, and I will fill it manually. It's very easy, you just adjust the SOP a little bit. Maik said, just put a waiting time. I have 8 seconds to fill in new water. Sometimes I tend to forget because I talk so much, but I try to remember putting fresh water after the measurement. So the first thing we do, we make ourselves a new folder. We don't want the old folder from the other group. We want an empty one. So we do it just like that. And of course, it's empty, no measurements inside. So let's change that. I was talking about the accessories with the tools to fix the water. We'll also have a USB stick for software, basically. If your software gets lost, you have the installation files there. You can install it on multiple computers. You'll have this, which we will use in 10 minutes, and you'll have this. So this is our internal standard F500. It's not a NIST traceable standard, so make no mistake. NIST traceable standards are very expensive. You can buy them from us if you want to, but there's no real need to. Because what happens with the instrument, whenever it comes from manufacturing, it goes first through the calibration. For the calibration, we use the NIST traceable standards. So we calibrate at different particle sizes to be everywhere perfectly within the range. But we also use this internal standard, which is not a real one, just one we bought a huge batch of and we always use. The reason we do that is we use it also during the final testing. So you have the results of the NIST traceable and this. But this we can give you, because it's not so expensive, we give you for free in the suitcase. So whenever you have questions about performance, you don't need to buy an expensive standard. You can use this first of all and check, does it fit with the final testing result that we achieved, or is it different? So if it fits, then instrument is fine.
We can reuse.
Yes, yes, yes. So you'll see, you have one package and you'll see how much I add per one measurement. It should last quite long, and even if that is empty, this is, as I said, not a very expensive thing to buy. If you use the NIST traceable standard, a single measurement, and I'm talking just about one measurement, will cost you more than 100 euros. So if you do anything wrong and you wasted 100 euros. So feel free to do so if you want. I'm happy, it's our money, but yeah, for a customer, I think it's not the best way to do this. So what we do to measure our F500. We go to a new measurement and we select the SOP, which I have altered a little bit in order to be able to manually fill this. We double click. The SOPs themselves are basically command based. So you just give the software a certain order of commands, which allows you also to freely program different procedures as you want them to be, which is actually for research, it's really, really a good system. What I will change here now, you see down below, there's our calculation, which I talked about, and we have it set to Fraunhofer theory. But I know this material very, very, very well, of course, because it's our internal standard, so we could actually use me theory. As you see now, we need these parameter-specific values. In this case, it's very easy because for a lot of materials, we have an internal database with these values. Of course, you will always find something which isn't in there. But you see, this is just, the list here is just aluminium. So you see there, I gave a AL, and he shows me everything that begins with AL. So there is a lot of materials inside. In this case, we choose this one, it's corundum, and now it's automatically filled out the values. So very important is here, a lot of times there are other companies which tell you that they can determine the values, because sometimes you don't know, like for your sample. You probably don't know the refractive index, do you? Probably not. You do? Okay, so, and it's very fine, so you will need it for the meat calculation. Now some people claim, yeah, we can determine it. Trust me, you cannot. We also have an add-on software where you can approximate the value. You can make a measurement, you can load the measurement in this, we call it me search, and then you can search different me parameters, and it will show you the results and the according measurement error. So it just looks where's the measurement error the lowest, and that might be a good value for the me parameters. But if you just go on the internet and you Google for refractive index, you'll find so many different parameters from different researchers. It's not a trivial thing that you just go like this and you have a refractive index. So actually nobody in the world can tell you the exact value. If you have a university in, let's say, Karlsruhe, and they do experimental physics and they have 1.8 as their result, there might be a university in California that does theoretical experiments and their result is 1.7. It's, you know, not exact. It's something, and if somebody tells you with a laser particle sizer we can determine the refractive index, sorry, but they're lying. It is not possible. You can approximate it, you can get an idea for what works, but you cannot determine that. If you tell me that you can determine in 10 seconds what a scientist searched for in 50 years, well, congratulations, you seem to be a genius. So we use these values as these are, of course, from literature, and the most important thing is use the same ones. Once you find something that works for your sample, stick to it. That's the thing that counts. Make it comparable once you move forward with your measurements. Yeah? Don't change it over time, because, of course, if you change the parameters, your results are not comparable anymore. So in this case, we just start here. Now we can enter a name for a measurement, like, for example, F500. That's the name of the material. We click OK. First thing that happens now, we will adjust the detector element. You will see here the live signals, and he's putting the detector in a position where the laser beam, the original laser beam, is the highest. So the best position for the detector is always done before every measurement. It is aligned. Now we have a dart measurement, no laser, just flat signals. We just measure electrical noise. And the next step is we switch the laser on and measure our background. There you see the first channel is always a little higher because it's right next to the main beam, so it always catches a little bit of stray light. So to get this completely dark is physically not possible. But that's why we take the background to actually deduct it from our measurement. So now we can add some sample. You can directly see here beam obscuration rising, so now we see, okay, it's not really close to 10%. We always start conservatively, so let's add a little bit more. Let's wait a little until it reaches the cell. And now we are in the area of 10%. So I'd say, okay, it's good. There's a countdown, which is preset in the SOP. Sometimes if you need more dispersion time, you can increase the time, of course. If you add too much, you can click this dilute button, and fresh water will come in order to lower the concentration, get back to a good level. And now we already started the first measurement. Talked about temperature control. You can see that up there, which temperature our system is at. And first measurement is already in. Second measurement is on the way.
Simple, karena memang yang mau dibaca kan
Tapi kalau untuk gambar nggak bisa. Nanti gambarnya memang nggak bisa.
yang satu lagi image sensor.
Yang ini enggak. Ini khusus ukurannya sama distribusi.
Oh, that's what I'm talking about. You have to be quick with the manual filling. That's why the automatic, if you have the automatic connection, it's much more convenient.
Karena nggak ada air di sini, jadi kita isi manual. Harusnya ada sumber air harusnya, jadi otomatis.
So that's our result. 3 consecutive measurements. The goal of consecutive measurements is to make sure you have a stable dispersion. I would say we have a very stable dispersion. As you see, they are all exactly the same. We can also check this in values. If we simply add a percentage chart, 10, 50, and 90%, you see the difference is rather small. Actually, the other group was better, but I forgot here to switch on the ultrasonic. On the other group, I had 50% ultrasonic power, which looks like improved our dispersion, but nonetheless, this is still absolutely a good result because
Oh, di dalam, dibawa ke dalam.
Jadi nanti dibawa yang ke dalam.
Iya, baru dibaca di selnya, baru dibawa ke sini lagi.
so
Ke dalam. Di dalamnya kan selnya di dalam.
Berarti emang ada penampung.
Oh enggak, nanti udah selesai. Kalau dia kita cleaning, dia dibuang ke sini ke waste. Ada penampungan.
Berarti yang kalibrasi tadi nggak dapat digunakan lagi dong, Pak?
Iya, sekali pakai itu doang, tapi kan sisanya masih banyak. Dikit ya.
So to give you an idea, you see here the variation coefficient between our 3 measurements. The ISO 13320, which is regulating laser particle sizing, gives you maximum limits for NIST traceable standards, that is, so they should actually come in more better. This is not NIST traceable still. The limits are 2%, 1.5, and 2.5, so you can see we are more than 10 times below the official limits, which is pretty good. In my opinion. As I said, in the previous one, we were even better with the ultrasonic, but that's really crying on a very, very high level. So in order to seize the last 8 minutes, I will directly start a new measurement, and we will now measure another completely different sample. For example,
Nggak nyampe 5 menit lah kali ya.
Itu dapatnya apa aja, Pak? Surface area, ukuran vertikal. Oh, ini ukuran vertikal. Diameter.
Kalau yang banyak juga kan ada biasanya deseteran segala macam itu beda alat ya.
Lamir.
Beda.
BET itu kan biasanya perpanjangan dari PSA bukan?
PSA beda sama PSA. Metodenya.
Ini yang tadi
Sekarang ini jarak mengukur contohnya
Cairan.
ada yang nanya emulsi. Kalau ini di Clara ini dia mengukuran fat globulnya.
Oh, sama juga.
was not enough, huh?
Jadi cendol.
So maybe you can clean this, and I will use this for the next one. Too much? So now we could, on the automatic dispension, we could use the dilute button. Yeah, the coconut oil is tricky because it's smaller.
Terlalu kental soalnya merah.
Itu tadi sinyalnya kebaca double.
Iya.
Yang di bawah 24, below 24.
Yeah, 10 to 25 usually. I accept, personally I accept anything between 10 and 25.
Nggak akan terbaca ya.
Selnya ketutup semua karena ketutup sama
The interesting part about this is it's not only biological, but it is a mix of dispersion and emulsion. So in the coconut oil you have, as I said, our milk, it has oil droplets, but it also has fat, but it also has solid particles in coconut. So that's actually a quite nice mix, but it still works very, very nicely. So it's a very, very stable system. And while it's, oh no, I need to do the cleaning. Actually, I don't have my hands free for checking. Yeah, I'm not used to this because usually I use, of course, the automatic procedure. So, these are two usually very, very simple and easy samples. Let's check the coconut milk. So compared with the F500, you see it's a finer material. The coconut milk is much finer, especially we will find also things here even below 1 micrometer. That's also the reason why it was quickly more beam obscuration with less sample, because we had smaller particles, as I explained in the beginning. But again, the same thing, very reproducible and 3 times same results, so very, very stable system here. What I actually would like to do, show you also a difficult sample. I didn't manage on the previous group, but maybe at the end of the day for all groups together I will show you one really difficult one. I will start with a more difficult right now, which is this carbon black. So I actually know this sample, that's why I brought it, but this would be the procedure we are doing now, would be a standard procedure for every unknown sample. So if you give me your sample, I will do the exact same thing. I will never add it directly there without knowing what it is, without knowing how it behaves, without any experience in measuring it. Never, and I show you why. So let's take some water here, put it in our beaker, and now add this carbon black. And the reason we do this is we want to see how it behaves with water. Does it disperse? And of course I picked this carbon black for a reason, because you see it doesn't disperse at all. It's just staying on top of the material of the water. It's just swimming there. So if I directly add it there, I will have all the particles swimming. Maybe some are dropping down and I will measure them, but it will definitely change also over time. More and more will drop, so the dispersion will be a changing dispersion during my measurement process. So this is definitely something I don't want. So the question is, you see down below it's still clear water with just a few particles, and also those are not really nicely dispersed. So this is a good example of some need to adjust. Let me clean this. How can we adjust this? And we talked about this a little bit. We need now something to change the chemical behavior of the water. In our case, we take the dusazine from the suitcase. We add this to the suitcase. This is really the last solution. So usually I would first take sodium pyrophosphate, which is very, very less strong than this one. This is ultra strong, really ultra strong. The right way to use it would be diluting 1 drop on 20 milliliters of water. From this solution, you can put a couple of drops in your dispersion. That's enough. So this is very, very strong. However, I will overdo it a little bit now on purpose just to get the point through. So if you check here on our dispersion, really pay close attention what happens once the dusazine touches the water. You see, it breaks the surface tension of the water immediately and the sample starts dispersing. So now, you know, I just need to, and there you go, now we have a dispersion. Simple as that. However, as always in life, the advantages mostly come with disadvantages. So you could think, now, hey, let's add it to every sample, just to be safe, we have a good dispersion. Of course, this is a surfactant, so like a soap. What it will happen is the water, the dispersion will start to be foamy. So what does it mean when it's foamy? It means there are air bubbles in the water. And then, of course, what can happen is that if your pump speed is too high, you can suck air bubbles in your system, and air bubbles will, just as particles, diffract the light, and he will show you the size of the air bubbles. You're, of course, not interested in the size of the air bubbles. It will basically disturb your measurement. So that's why you also have to be a little bit careful. On the previous group, we saw no air bubbles, so Yeah, I actually would like to see some to get my point through. I mean, it's not always about having a nice measurement, it's about showing real life experiences. So let's just go and call this carbon black, and then yeah, I have more stuff here. Actually, the one I would really like to go with is the soil, but maybe we'll do that for all groups together once at the end, because this is something where you can really see shifting results because of clay particles sticking together and then over time breaking. That I think I mentioned that geological departments always put this in external ultrasonic before measuring for at least 5 to 10 minutes. So, but anyhow, even when I shake it, you see air bubbles on the top. You see it's already starting to be foamy, and when we add it here, this will probably, you see the air bubbles, you see the foamy. Oh, I think I didn't add enough material. So well, let's see where we go. So this is, you see, also a good example. I still have some from the previous group, so I can just add this. So now it looks good to me.
Dan ini kan ada di background dulu sebelum ukur. Kalaupun masih ada partikel itu dia menolak sendiri.
Can you put this in the waste and clean it with a paper afterwards? So 10% looks good. Okay, not so many air bubbles. Actually, I don't think we'll see some. Would be nice to do so.
Ya, makanya sebenarnya flowing terus. Jadi artinya kalau kamu khawatirnya ada barang aneh masuk ke dalam sini kan di flushing terus. Cuma kalau ini udah ditutup gitu ya? Iya, tadi ya kan pokoknya cepat sekali. Enggak ada. Oh itu otomatis. Iya, otomatis di flushing. Tuh ini kan buang sini. Lari ke sana semua.
Apa yang terjadi kalau misalnya airnya habis, Pak?
Now you see, after you have so much soap or detergent in, I would actually do another 2 or 3 times cleaning. You see, it's still foaming. It's still some of the detergent in there, so it's not optimal, but for our purpose should be fine.
Kalau dianggap kurang, bisa kita cleaning lagi.
No, it's a typical thing in life. Whenever I want a good measurement, I might see air bubbles. Whenever I want to see the air bubbles, I don't, and I get a perfect measurement. So yeah. But usually what would happen is, if you see a peak around 200 microns, this is a strong indication for air bubbles. Of course, you can also have sample there, but in this case, we again have 3 perfect measurements. Unfortunately, I would like to show you what it looks like when it doesn't work properly, but here it's also really good, and unfortunately, we have to again shift to the next group, but after 3 o'clock I will still stay. You can stay, you can come in and we can do some other. You're welcome.
Can you back again to the result?
Of the
Result?
which one?
The last.
The table in the end.
The carbon black.
Yeah, carbon.
Yeah, this is carbon black.
See us for
No,
the user
the table.
Table.
Specific. What the meaning of this one?
Okay, wait, I'll explain you. So basically, this is the D values, percentage values. So the D10 means that 10% of the carbon black is smaller than 6.5 micrometers. And 50% of our material is smaller than 21.7, and 90% is smaller than 61.5. So you can also see this here as a table for sizes. So in this, you have the size first. For example, 10 micrometers. You see 20% of the sample is smaller than 10 micrometers. Already 56% is smaller than 25 micrometers. So you see it's a big chunk of material between these 2 sizes. That's basically how you read the tables. And to be fair, we showed the last group, I'll show you as well. If you want to print a result, you can really quickly do so, and you get a PDF with your particle size distribution, which is editable and customizable.
Oh, kita dapat hasil kayak gitu.
Iya.
Oh.
You save that, you put it away.
Min. Iya kan bener. Iya min. Iya tuh.
Iya.
Betul. Min.
Oke.
Maksimal.
Thank you.
Thank you.
Tinggal punya.
Iya tinggal punya belum.
How many groups we have? 4.
This is the last group, I mean, the last group.
Last group already. Okay, the lucky group, because then we can,
But maybe 10 people.
10 people, it's okay.
yeah, sure, ask them if that's okay. So now I'm not in such a rush. We can relax, go slow, take half an hour if I have to. That's good. So, same thing as with the other groups. We start with the hardware, show you basically the delivery state of the instrument. It comes, of course, in a box, but once you take everything out, you'll have what you see here. So fully equipped with a monitor, with the computer, pre-installed software. So you just plug it in, start the software, you're ready to go. You get the keyboard, the mouse. One thing you see here, we mentioned the ultrasonic box. So this is just attached here to the back of the dispersion unit. So it's a module. If you don't need it, you don't have to take it. You just then have this part without the silver box. It also works. And you see here the drain for our cleaning when we want to flush out the used dispersion. What we are missing here on site is actually the water connection. So we have no tap in this room. Usually there's also a hose that you connect the tap water or whatever water source you have to the instrument, which enables you to have everything automated. You basically just press start, add sample, the rest will be fully automatic. So you can basically leave when you come back, you have your result, you have your clean water in again, and everything is done fully automatic. We don't have that luxury here. We don't have water supply. The good thing is we can improvise. I changed the standard SOP in a way that I will have about 8 seconds to manually refill the water here from the front, and that basically does the same job. It's just a little bit more inconvenient to do it manually, so that's why actually the automated water supply is much better and much more convenient. One more thing you'll get with the instrument is the suitcase with accessories. So the tools are basically for connecting the water, because you want to clamp that very firmly so that no leaking occurs. So that's why you get some tools in here. You will get a USB stick which contains everything you already have on the computer, just in case anything happens to the hardware or it crashes, or you never know. Computers, yeah, Windows, hey, what can I say? So this is basically a backup of all the stuff that is also delivered pre-installed. You'll get this thing, which is a tenside or surfactant. We will get to this in a couple of minutes. You'll get some cleaning powder, you get some wipes in order to clean the cell, if so desired. And what we will start with is this. You also get this in your accessory suitcase, and I will explain you now what this is. So when the instrument comes from the manufacturing hall, which we saw on one of the first slides, it comes down to the final testing department. There it's calibrated. That's the very first thing that happens, because you will never be able to manufacture 2 instruments in the exact same way. They are all, of course, slightly different. That's why we have to test them in order to make sure they give us the same results. This final testing is done using the NIST traceable standards materials. So they are quite expensive. We use several ones in several size ranges, and with them we calibrate the instrument to be measuring perfectly fine. At the same time, you also use this. This is our, you see the Fritsch sticker, our internal standard. So it's not NIST traceable, but the thing what we do is we bought a huge batch some time ago in order to prevent the batch from changing. So we always have the same batch and take small portions of it. We also measure this during the final testing procedure. The advantage is we just give you this for free. So in case you ever come across strange measurements and you want to know if is it the instrument or is it your sample? You don't know by an instance. Go measure F500, compare it with the final testing result. If it comes the same, the instrument apparently is working the same way as it did when it left the company. If it is not, you apparently have a problem and contact our service. 95% of the cases, the simple reason for not being the same is it's dirty and you need to clean it. So that's the most common reason actually that happens. So why we give you this is you could of course use one of the NIST traceable standards, which we use for calibration, and measure that. But that will make us very happy, but not you, because these come very expensive. So just a single measurement of one standard will cost you at least 100 euros, minimum. So if you waste it, if you do make any kind of mistake adding that sample, you wasted 100 euros. So you can buy the next step. If you want to do that once a year with all NIST traceables, you see the cost is amounting. So we want, I mean, this instrument doesn't come cheap. It's not for free. We know that. So what we want is you buy it, and then you're happy for the next 10 to 20 years. And this is one way we can ensure that you have a possibility to check and to do everything without constantly spending money on the way all the time. So, of course, this can be empty at some point, but here the entire box is, I actually have no idea, do you know?
The price?
Yeah, I think it's, maybe the entire box is below 100 euros. But this you can make thousands and thousands of measurements with. So that's the reason why we use the F500. It's namely, the material is actually corundum, aluminum oxide. So it's also very stable. It's a material that disperses very, very well and very, very easily. So you probably will not have any dispersion issues with this. And I think we start with this. Let's start with the easy stuff. What we do is we are here in the main menu. So the first thing, there are the folders of the other two groups. We don't want to use them. We use a new folder. Let's call it another name. And then we open our measurement folder, which we just created, which is, of course, empty. So what do we need to do to fill it? We need to click New Measurement, and now we can select an SOP. So you can, of course, manufacture or write your own SOPs for different materials and so on. The way the SOPs work, they are a set of commands. So you can program them very freely. In the software, you'll find certain commands, and you can just add them to one another, and that way make your own procedure. Something that I will change now in this, first of all, I will add ultrasonic power, 50% for the dispersion. So the ultrasonic has 50 watts, which is a lot. So 100% would be quite strong. Let's go with 50. And the next thing you see down here, that's what I talked about in my presentation, the calculation of our result. Here it's set to Fraunhofer. For this, as I know this material, of course, very, very well, we can use the Me theory. As we know it's aluminum oxide, it's corundum, and we also know more or less the parameters for that. You see, once I choose Me theory, I can now here select the material-specific values. In this case, it's very easy because I just can click here under Solid, and it opens a database. So this database is always included. Of course, it doesn't contain everything. You see, this is just the materials which start with the letters AL. You can also add your material there. So if you don't want to add the numbers manually every time you add your material, you can automatically set it in SOP for your material. And now we choose here aluminum oxide, and you see the values are pre-filled. One very, very, very important remark from my side regarding these Me parameters. There are other manufacturers, and I've come across twice so far, that a customer tells me that they were told by the other manufacturer that they can determine the values. Well, I want to see that. Because also we have an additional software here on the computer, which is called Me Search, with which you can approximate the values. But if I told you you can determine it, I would be lying. The reason is if you go on the internet and Google for refractive indices for different materials, you will always find different values. Maybe the University of Karlsruhe did experimental physics on it, found a value of 1.8. UCLA in California maybe used theoretical approaches and found 1.7. So these are actually not fully determined. Scientists in the last 100 years have done research to find refractive indices of materials, and this is quite a complex thing to do in physics. So if anybody tells you they can do it with a laser particle sizer, no, they can't. They can maybe find an approximation just as we can. We can load a result of any material, of any measurement into this MeSearch software, and then we can enter certain areas or certain numbers. For example, look between 1 and 3 for the refractive index, and it will go through all the different values, calculate the results, and look where the error of the measurement is minimal. And then it will give you this value. Just because the error of the measurement is the smallest, it doesn't mean it's the right refractive index, okay? That's very important. It just gives you a hint, just gives you an idea that this might work quite well. And for some materials, there's no other way. If you have a compound of many different materials, it's impossible to determine the refractive index, but you can approximate it. So this is very important to understand. It's just an approximation. Yeah, just don't take it for granted. If, for example, I had this once using the MeSearch, and I looked for the values, always got bigger, 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 and I found the minimum error at refractive index of 20. So just, yeah. Although my studies are a long time ago, I can think myself that maybe a refractive index of 20 might not be the right value. So, you know, that's why I'm just saying you have to be careful. You have to use your brain a little bit and also go with reasonable parameters. So anyhow, we choose these ones, and the next step we do is we click Start. Now we can enter some information. I will limit this to the name of the material, which is F500, and I click Start. First thing that is happening, we will do an alignment now. The detector in this instrument is actually movable. You heard that maybe? That was the detector moving in the perfect position in the middle where the laser beam hits, because if I change the liquid, I change the refractive index, I change the position of the laser. It's a dark measurement first, you see no signals. Next thing is background measurement. Now you see some signals, because this detector is right next to the main beam physically, and it always catches some stray light. But for that reason, we do a background measurement, which we then deduct from our actual sample measurement, speaking of which, we are ready to do that. So now it tells us enter sample now. Here you see the beam obscuration. So this is what we want to be, I mentioned, between anywhere 10 and 20 or 10 and 25. So if you don't know about your sample, you always go careful first, and when you see it's not enough, you just add a little more. So now we wait again, and we see, okay, it's slowly rising. Maybe we add a little more. This should be enough now. So as soon as we reach 10, we can actually stop adding more sample. Maybe still a little more. It already starts. So there was a countdown. I don't know if you saw it on the left, lower left, which you can preset in the SOP. I think the standard setting is 30 seconds. In case you need more dispersion time to stabilize, you can, of course, also increase this. First, so we are doing 3 measurements here, each 10 seconds. First one is gone through. Second one will be in a matter of seconds. There's the second one. And the third one is running, which tells me I may get ready for the automatic, the manual. It's a little inconvenient. I definitely prefer the automatic way of cleaning. But without tap water, what can you do? I have to do the job here. There you go. So about time to check our result. So that is the result of our F500. The first thing what we want to know, and that's why we do 3 consecutive measurements, we want to know if our dispersion is stable. I'm pretty sure it is. As you see, we see only one chart, and the reason is they actually cover up one another perfectly. So the repeatability of this material, no surprise. I mean, that's why we use it as a standard, because we know it disperses very, very well. We can also have a look now at our percentage values. So for example, D10, D50, D90. So 10% of this material are below 8.6 micron. and 50%, half of the material are below 17.3. You see the reproducibility here, the variation coefficient. Just to give you an idea, the ISO norm limits 2.5%, 1.5%, and 2%. So as you can see, we're more than 10 times below, even with a non-mistraceable standard, which is quite nice. Also, we can add a size table, for example, this one, and then it tells us that around 10 micrometers, we have 15% of the material smaller than 10 micrometers. 78 is smaller than 25. So actually, we should add here for this material, for the F500, a few more sizes in between, which, by the way, is easily possible. So the user values, these tables, which I now added, in the main menu, you can create your own. So you can create endless customizable tables specifically for your material that you also get the values you want. So it's not something that is just there and you can't change it. You can customize all of this. Unfortunately, of course, our time is a little bit limited, so I cannot show you all the features which are available in that software. Okay, F500 comes in pretty nicely. We created a dispersion with this, put it away, and move to the next sample. So what we have here, this is then an organic example. We just bought some coconut milk. Coconut milk is actually also quite special in a way that it consists of both a dispersion and an emulsion, because you have fat and you have particles. You have both, which usually would make it more complicated. I mean, I know the coconut milk actually is quite an easy sample. We will come to more complicated later, but just to show something organic, something very common, which you just go to the supermarket and buy. Of course, the manufacturer might be very interested in the particle size because he wants to have the same product over and over again in the manufacturing process. If he sees that from batch 1 to batch 2 he has a significant change, I can tell you the most thing that will change is the taste. Because the particle size has a very big effect on taste. That's, for example, chocolate manufacturing. Everybody has eaten chocolate before, so it's a very good example. Probably you've had a very good chocolate once. You also have probably tasted a very bad one. The simple difference between good and bad chocolate is particle size. The smaller the particles, the better the chocolate, because the smaller the particles, the better it will melt and create flavor in your mouth, on your tongue. So that's basically the only difference between a good and a bad chocolate. I don't know how about the coconut milk, but might be pretty similar. So we do the same thing again. In this case, let's just go and start. Call that thing coconut milk. And go. Same procedure again. So first we do the alignment of our detector array, then we do a dark measurement, then we do a background measurement, and then we start giving the sample in. It's actually very important to monitor your intensities. You see these are the 51 main detector elements and then the large angle and backscattering. Because in the background measurement, if you see intensities in this area, there's a pretty strong hint that you have dirt on your glasses. So it should be nice and flat as it is here. That's the way we want to see it. Now this will be much finer, so I will have to be a little bit more careful with giving sample in and not adding too much. Oh, it's empty. I thought somebody, it looked as if somebody already put some milk inside. So nonetheless, let's just add a drop. This might be enough already. Yeah, looks good. Oop. So there you see the countdown I mentioned. You can, of course, end the dispersion process manually as well. Or you can also, if you add too much, you can click dilute. Of course, only if you have tap water connection, then he will dispense some of the dispersion and get fresh water in order to lower the concentration to get your desired beam obscuration back. So in that case, it looks actually nice. Here you see also the aforementioned temperature monitoring, which is very stable, which is nice to have. And now first result is in. Third measurement on the way. I should get ready for the cleaning. So, again, very nice results. It is an easy sample that I have to admit, the coconut milk. It's a little finer than the F500, so if we check the values again, see now the 50 is around 7 micrometers, our D10 around 2. But again, 3 very nicely reproducible results. Actually, from the variation coefficient for some natural material, quite good. But it's not always that easy, of course. I mean, it's nice that I had 2 samples now, and they are both very nicely reproducible and very easy to measure. In real life, of course, you sometimes encounter difficult samples. I have just one example here, and now both measurements I made, I directly put the sample in. I did that because I knew both samples. I knew both were easy to measure. I knew the behavior of both in water, but in many cases, you'll get a sample which is new. And so the first thing you always want to do with a new sample, you never want to end it directly into your unit. You always want to take a beaker, fill it with water, and then you take your sample. Which one was the open one? This one? And what you do is you first check the behavior of your material in water. So let's put, this is carbon black. And I choose this, of course, because it is a very good example of a hydrophobic material. As you can see, it's not really dispersing. It's just swimming. And even when I shake it, it makes things worse because it sticks here to the side of the beaker. So you can imagine if I add it directly, same thing is going to happen. Over time, it will maybe sink in as it does here. If you look slowly, some particles sink in. But this is not good because that means it's changing. That means during our measurement, it's changing. And that's something we don't want. We want a stable dispersion. Why are these so beautiful, reproducible? Because we have stable dispersions, or in this case, even emulsions. So that's why it looks so good. If it's not stable, it will most likely not look so good. And the solution for such a sample is an additive. I would never in real life use this first. This is the one we give you in the accessory suitcase. This is ultra strong. This is really, really strong. If you order a second dose of this, you made a mistake for sure, because you wasted. The procedure of using this is 1 drop on 20 milliliters of water, and from that solution, you can add a couple of drops in your dispersion. So as you can see, this should last very, very, very long. And I would first always go to something like sodium pyrophosphate or some less strong surfactant, because I will show you in a minute what can happen when you use too strong, and I will actually just for demonstration purposes, go a little bit too hard on the Dusazine. I will take an entire drop on this. Did I actually touch it? On the spatula. Just to show you, if you look now at the material on the surface of the water, what happens when the surfactant touches the water. Attention, magic moment. Boom. It immediately reduces the surface tension of the water. And now I just shake a little bit, and all of a sudden I have a dispersion. Still on the walls, because I shook it before some material stuck. But as you can see, now I have a dispersion, which I can measure, which can be stable. The downside to this, that's why I'm saying never use this as a first option. A surfactant, and you might know that from washing the dishes, will of course create foam. And also this will create foam. But if you have foam in your wet dispersion, what can happen is you can, with a pump, suck in air bubbles. When this air bubble goes through the measuring cell, it will diffract light just as a particle will. So you can actually be measuring air bubbles. And I can tell you the size already. I know it's around 200 microns, but I'm pretty sure you're also not interested in the size of air bubbles when using this equipment. But it's just something you need to be aware of and you need to take care of. So that's why you need to be very careful with this material. On the other 2 groups it actually worked, although I put so much in. Both measurements went without air bubble peak, as it always is in life. When you want to see it, you don't. When you don't want to see it, you do. What can I do? So maybe I should promise you perfect measurement now, and maybe then it becomes imperfect and we see air bubbles. Who knows? Let's just check We again make a measurement. We just leave all the settings the way they are and just call this now carbon black. Hope it's enough, but we'll see. Again, same procedure, first the alignment, then the dark measurement, and background measurement. So also when I fill this, when I put this in, pay close attention. I'm pretty sure once it's in there, you will see a little bit of foam coming up in the wet dispersion on the water, which is an effect, of course, of the dusazine of the surfactant. So let's check. There you see already some bubbles occurring. Oh, I probably can add all of it. Yeah, let's add all. It's barely enough. See, I still have some from the first group, so I can add that as well to give us a little bit higher beam obscuration. So now we have a rather low pump speed with 40. If we would be measuring that at 70% pump speed, we would definitely create more foam. So that's always something you have to monitor, your settings. Ultrasonic, pump speed are the most basic ones. And yeah, again, no air bubbles. So typically, if you see a peak around this area, it's a hint for air bubbles. Of course, it can also be that your sample has agglomerates in this area, so don't take for granted whenever you see something there, it's an air bubble. But when you do have them, it's usually there. So again, 3 reproducible measurements, not as reproducible as the previous 2 samples. Already here you can see a difference in color. So, okay, it's not that bad actually. It's a little bit higher than the other ones if you check the variation coefficient, but still pretty nicely. If we had measured that without the surfactant, most likely we would see a bigger change because the dispersion would not be as stable. It would, in the beginning, be less particles, then they would start to sink. You never know what stays on top. Probably the small ones, and the bigger ones start to sink, while the smaller ones still swim. So then you will definitely get a change in results, and that's the common issue. You just measure something, you throw it in directly, measure it, you get 3 different results. You're asking yourself, why is it not measuring properly? Of course, it's measuring properly. You're not feeding it properly. That's in 99% of the cases the issue here. So let's now say we have a measurement which we also want to send somebody or which we want to use. What we can do is, we have our tables already in, real quick and dirty, just print, select a report. It's all customizable also in the software, the report's editable. And then you have a PDF with your chart, with your values. You can save it, you can use it, you can publish it if you want. So that's basically the next step. Of course, there are many more features in here which I could show you, but which we don't have the time for. Since you're the last group, you're also lucky enough to have 7 minutes more already than the other groups. But I think at that point we close, but we still have time. If there's anything you're interested in, anything you want to see, we'll definitely stay here a little longer. Also, some people had samples which they would like to have measured, so I'll definitely stay a little longer to answer any questions that might occur or anything else you would want to know. But until this point, thanks for attending, and so it's all yours.
Thank you.
You're welcome.
Atau ada yang bawa sampel juga bisa dikasihin ke paten.
What we can do, I'm not a fan. I mean, this was all working very nicely. I'm not a fan of just showing the nice things. So actually I had my colleague bring from outside of the university some soil. Okay, I hope it's really just soil, and but already here you see, if you take that, it looks like it's big, but once you start crushing it, okay, some are really rocks, but some particles are actually really small. So, there are actually rocks inside. So we want to be careful. We don't want to add anything bigger than 4 milliliters because it will get stuck inside. So we should be a little careful. But let's try something, okay? Let's make a bad measurement. Because we did not prepare this. Usually you would put this in an external ultrasonic because soil needs a lot of deagglomeration. It's very prone to agglomeration. But we are now using for ultrasonic. Let's increase the pump speed a little and make a measurement of soil. So I'll try to not catch any rocks. Now let's pray there's no rock inside. Okay, I have a little assumption that will actually work too well, so let me end it prematurely before we get a stable dispersion, just for showing you how this can also look like. Because it's actually dispersing much better than I thought. Damn it. Way too reproducible. Okay, a little shift we observe. At least I can make my point here. So to be honest with you, to look at this, I actually thought that we will get a big shift from first, second, third measurement. It's not as big as expected, but you do see a shift. So especially, okay, the first two were actually quite stable, but the third one, the blue one, you see we observe a slight shift to the fine range. What is missing in the third measurement? You see here on the coarse part, there's something missing. So that is basically the ultrasonic still destroying agglomerates of clay, making them smaller. I actually expected it much, much worse, so, but still you see it's happening. If you look at the numbers, you see first measurement D50 34.0, then actually it gets a little bit bigger, but the third one it gets much smaller here at 32.5. So you see it's not as reproducible as, especially compared to the first three sets of measurements, which were really, really nice. So here it's not that nice anymore. Simple reason is, I on purpose also started the measurement earlier, we did not have a really stable dispersion yet. So that's why also this material I would always put in a beaker, put in an external ultrasonic, prepare it really nicely, and then add it. And then, this is also an easy soil sample. Unfortunately, you have easy soil. We also tried that in Jakarta. It was also easy. Soil that becomes really difficult is like sediments in lakes or sea sediments, because they not only have mineralogical parts, they often have biological parts, fibers and stuff like that. And then it becomes really, really difficult. And sometimes with these samples, you can do the utmost preparation. You will still not get a reproducible and stable dispersion. You will always have a little bit of a shift. With some samples, you just have to live with it. You then, for example, I would recommend, see here, he creates a mean and average of all three measurements. In that case, maybe make 10 measurements and take the mean, take the average as a result. So that would then, in that case, be my recommendation to go with it. Yeah, of course we can't do everything in a couple of minutes, but this is a short glimpse of possibilities. Actually, wasn't this really small, the coffee? We have measured that already, so let me just check. Was it Tropicana? No, it was drink. How did we call this? Do you remember? What's the name? Yeah, cappuccino, it should be called, huh? I don't find it. Drink somewhere we had it. Because we measured this cappuccino before, I just want to know, I think it was rather fine. No idea where it is. There. Okay. Maybe I would ask the people who had samples with them.
Mbak, sampel yang tadi Mbak, yang nano solution.
This looks familiar, but I had similar stuff from mining companies, so I'm very glad it's your instrument now, because this is stuff where you really need good cleaning afterwards. But do we have soap somewhere so we can, before we pack everything, we can clean everything properly? I can also demonstrate them a very easy and simple way of cleaning. That's also good. If you can organize me some soap? Just regular soap is okay.
Hand soap, right?
Hand soap, right?
Huh?
Hand soap.
For example, if you dishwasher would be perfect, but hand soap will do the job as well. So this is already a dispersion as it looks like. So that's good. May I open it? Could we get we have a clean pipette. Perfect.
Is it clean?
What's the material?
Magnetite.
What?
Magnetite.
Magnetite, okay. No experience with that. Looks very much like, you see, of course, we actually do the first mistake. It's all sedimented. So usually we would now prepare this, again, external ultrasonic to get the sediments off the ground, because this will not be representable of your entire sample, because some parts are sediment on the ground, the others are still dispersed. Nobody knows if there's a difference in size between the stuff on the bottom and the stuff still in the, is it dispersed in water or in what?
Ethanol.
Ooh, okay, I would actually measure this in alcohol then, better, because if you add the ethanol, it will of course change the liquid itself, which will change the refractive index of the liquid. Let's try. Let's see. Okay, let's just add it like this. So, as I have no idea what it is, I will also again just go with some random settings, make the first measurement. You enter the name maybe. I have no idea how you write it. Oops. Okay. So it is, yeah, that's what I thought, a mineralogical sample more or less. So looks very fine to me, so we have to be very careful. Oops. See, that's about careful, as long as it doesn't get on the clothes. So let's see. There you see the ethanol. You see how you have these. You would always want to measure in the liquid that you have the predispersion in. Because what will happen probably, or very likely, is with the ethanol we will change the refractive index of our liquid. So once we change the refractive index of the liquid, we will change the path of the laser. And if the laser then, instead of the original position, goes slightly to the direction of the first element, it will basically be the same as if we have a diffraction pattern from a big particle. So this could be that the algorithm now just calculates us very big particles. But actually, it's just the ethanol which changes the refractive index of the water and shifts our laser beam to that side. So that's why if you disperse it in ethanol, pre-disperse it, you should also measure it at least in some kind of alcohol in order to make it similar. No, doesn't look too bad actually. So especially on a trial like this, before we pack, we definitely want to do some good cleaning.
Your tea.
Oh, thank you. I was asking for soap, but I'll also take the tea, no problem. So what we are doing here, we're not just adding different kinds of samples all the time. We're adding some dusazine, we're adding some ethanol, we're adding loads of stuff. So after such a 3-hour experiment, I would definitely do a good cleaning to get all of that stuff out, because you never know where it settles down, where it sits, and later on, you know, you let it stand after a week, you come back, you make a measurement, you wonder, why do I have strange peaks? Why are measurements not reproducible? What's going on? Yeah, probably there's some residual of all this stuff somewhere inside, and then it comes out slowly, disturbs your measurements. So that's why cleaning, I can just repeat myself, is very important. Actually, not as bad as expected, but you see a real-life sample, so we don't get the super-duper reproducibility which we had in the beginning. What I first look at is we obviously have a bimodal distribution. So the main peak here is around 2.5, 3 micrometers, but we also have one here around 20 micrometers, a smaller one, which is not stable. So really the difference between the 3 curves obviously comes from this 20 micrometer peak, which seems to shift. So my first thought when I see this is there might be agglomerates which over time are getting smaller, although this would then mean we had ultrasonic switched on, that from 1 to 2 to 3, we should see particle size getting smaller. So let's check that if that holds true. Actually, it's the other way around. As you can see, it gets bigger. So that is something now we should ask ourselves, how does that occur? So seemingly, I mean, the difference is not really that dramatic, so I'm not shocked, I'm not like, on my heels, but still we see that particle size is getting bigger, which is not really explainable on the first side. What could happen? So the next thing I would do now, I would take another SOP. Yuri, you made one where you have 2 sets of measurements, remember? Was this the last one, SOP for manual fill? The one you programmed yourself, remember? I think it's this one, huh?
Yes,
oh, I can actually just check it. So he, on the training, was actually very, very good at making himself an SOP where you have 2 sets of measurements. So what we can do now is, you see, we start without ultrasonic. Then we will make 2 measurements. Yeah? Then we will wait, maybe not 4 minutes, let's wait 60 seconds. And then we will make another set of measurements with ultrasonic power of 100. So we will have a comparison with the same exact aliquote, no ultrasonic, super strong ultrasonic. See what happens. So because we are now, after the first measurement, a little bit tapping in the blind. We observed something, not dramatic though, but we observed some change. And we're not sure where does it come from. So we take the next step. We compare a measurement with and without ultrasonic. So we started, was it FE304? There it is, FE304, yeah. Looks okay, so try again. course, as I mentioned, a very disturbing factor is mixing ethanol with water. That's not ideal. One more drop, what do you think? Try a small one. It was not so small actually. So now we're making 2 measurements with no ultrasonic, and after that the ultrasonic will switch on, and we will wait 60 seconds in order to give the ultrasonic some time to work, and then we'll make another set of 2 measurements. Actually, the first 3 measurements we made were at 50% ultrasonic, so you can already, in the meantime, have a look at results. So first difference we see without ultrasonic, it's more coarse. So these are the measurements now without ultrasonic compared to the 3 measurements here with ultrasonic. First hint would be ultrasonic has an effect, but let's wait on the next set of 2 measurements to really confirm this is the case. You can also see we used so much dusacene, we still have not flushed out all the dusacene apparently. It's still a little foamy, a little bubbly on the surface of our dispersion. Wait, I need to clean. Let's have a look. So we definitely see a change. You see first set of measurements, second set of measurements. Surprisingly, this peak shifts a little bit more to the fine range, while the big peak actually did not really exist without ultrasonic, very, very slightly. With ultrasonic, it gets bigger. So first hint, the ultrasonic seems to have a contradictive effect. It's not really making it smaller, it seems to make it bigger. I've observed this once. Actually, let's compare to the measurements with 50. So that's 50 and 100, and we see, yeah, with 100 it's getting bigger than with 50. So here the ultrasonic has the opposite effect. I've seen this once with also a mineral with a feldspar, which is a mineral consists of layers. In that case, the higher you go with the ultrasonic, you put electrostatic charging on these particles and they start to stick together. I'm not sure about your material, I've never measured this material, but it seems to have a little bit of a similar effect. That with the ultrasonic, we seem to create bigger particles. Just slightly, I mean it's not big, but there seem to be more, and it's very systematic, because you can see with 100, it's quite reproducible, very reproducible. Also, the same goes without the ultrasonic. It's quite reproducible, but if we compare with and without, there's definitely a shift going on. So here, it's actually a very nice sample because it shows us that the setting of the ultrasonic moves our peak. It creates, from these small ones, it creates big ones. So I'm pretty sure this could be a similar effect. I don't know how about the electrostatic properties of this material. You think it's very prone to electrostatic charging by outer power input? Or, I mean, since it's iron containing, it's quite likely. This is just the first hint we get, so that we somehow have some effect of the ultrasonic. Because another thing, what could happen, of course, if we just compare electrode 1 to electrode 2, maybe because it's sedimenting so much, with the pipette we take a different fraction with this different. But this is, of course, we excluded this possibility by using the exact same electrode and changing the parameters. We obviously see that the parameter, in this case the ultrasonic, has a significant effect. Actually, it's not that significant if you look at the user values. So we have 2.9 shifting to 2.6. This is not really such a big a deal. But if you look at the D90, there you see it much more. So here we had 8.5 or 8.3, and we shift that to 9.4, 9.3. So we actually increase the D90 by 1 micrometer using ultrasonic. That would be a nice research project for a master thesis or so, to explore the effect of ultrasonic on your material. Clearly there's some, but of course, in this case, what I would do most likely, I would do a couple more experiments, but the point where I'm now, I would guess I would just measure this without ultrasonic, obviously, because it does have an effect, and it seems to have an effect which is one we do not want. Yeah. So apart from that, it actually doesn't look all that bad. So we take these. This would be then without ultrasonic the way we would measure this. Of course, we did all this with Fraunhofer. So another step, which we really want to work with this, is some research. Find the refractive index and the absorption coefficient for this material. If you can't find it, use the me-search, run some iterations, look what fits, decide for some values, use them. They will probably, I can just give you an idea. So the nice thing also in the software is, let's say, okay, we used Fraunhofer. Now I'm telling you from the size range we're in, me would be more appropriate. So you'd think, now, okay, then let's make another measurement and use me. You don't have to. You can use the raw data, which we already have, and just recalculate that. So you just need to know your measurement number. That is, in our case, use 156. And now there's the SOP called recalculate. So we can now say we want to measure this with me instead of Fraunhofer. The only issue will be our values. So let's look for F. F, we only have fluoride, iron, then
Iron oxide?
iron oxide we have, yes. Should be somewhere. It's iron. Huh. Magnetite. There we have magnetite. So let's just try these values. Say OK, and the number was, I think, 156. And what you see is that's the original one. So that's the same measurement, exactly the same measurement, just the calculation is different. The orange curve was calculated with Fraunhofer, the red one with me. Also, you see where the effect takes place in the fine region. But in that fine region, you definitely trust me more than you would trust Fraunhofer. So actually, I would take this result rather than this. Of course, now we just use the parameters from the database, which probably our old laboratory boss put in there about some time ago. I would definitely go do some research on Google or on any research platform to find what is the results in science for refractive index for this material, okay, for magnetite. And then pick a parameter, go with it. Because the important thing is, at the end of the day, when you do your research, the important one is not really, is it because you see the number, the difference in numbers, is the D10 0.8 or 1.2, but the important one is, or D50 2.9 or 3.3. The important one is, when you start working, decide for one of the two, so you make all future experiments comparable to this one. Yeah, that's what really matters at the end of the day. But of course, you should pick the one that fits best. And I can just recommend use me. Go with this one for sure. Okay. So actually, not that bad a sample. Maybe a little dirty, so we should do cleaning. There was one more, I think, more sample. Okay. Yeah, I asked. Do they have 10 minutes for their samples?
I just have a question. So,
Yes.
I just wonder if I have another type of carbon, like maybe activated carbon or graphene oxide. So it is suitable for the liquid just used to us for carbon black.
This one you mean, the surfactant. Actually, I would never use this, as I mentioned in the first place. I would start with sodium pyrophosphate. It's also a surfactant. It's not as strong. Also will not create so many air bubbles. But usually, if it's also carbon, it will probably behave very similarly. So, the material. You mean your carbon or this surfactant? Well, I said 1 drop on 20 ml, and that you can use just a couple of drops for each dispersion. This will last very long. Trust me, very long.
Okay, thank you.
If you manage to finish this within 5 years, I'm surprised. You used way too much.
This is the end of the workshop.
Okay. Do we need to be out at a certain time or?
Okay, thank you Mr. Maik Paluga and Novatech team for your guide and demonstration. Okay, this will be the end of our seminar today. Thank you everyone for your attention. Me as a moderator apologize for any mistakes during the seminar. It is my pleasure to be here. That's all from me. Once again, thank you and see you on the next agenda.
Yeah.
Buat tambahan untuk teman-teman yang punya sampel juga, misal belum bawa hari ini bisa dititipkan ke Novatech, nanti bisa dapat hasilnya juga gitu. Mungkin bisa langsung dikomunikasikan dengan pihak Novatechnya. Nanti bakal dikirimkan hasilnya via WhatsApp group. Jadi misal ada yang belum masuk WhatsApp group nanti boleh info juga.
Ya nanti dioptimalin dulu.
Bawa sampelnya atau mau dikit? Oh, boleh. Sekalian kita bawa aja, tulis nama sampelnya apa, terus namanya siapa, nomor handphone sama email. Ya, boleh. Kenapa? Belum ditutup. Udah ditutup, udah. Oh, udah. Ya, gak apa-apa nanti sampelnya pokoknya kasih nama sampelnya apa. Oh yang di lab boleh. Kita di sini kok maksudnya mungkin sampai kan beres-beres alat juga jadi boleh.
Okay. Let me check your heartbeat.
Udah. Ya, makasih Bapak.
Terima kasih.
Very strong heartbeat, man.
Sudah mau datang seharian.
Time to vacation.
Take a picture I guess.
Yes.
Aduh, kapan lagi kan ya?
Di mana ya? Di depan atau di sini?
Depan Pak.
Naik, take you.
Yes. Huh?
Take a picture.
Yes. They shall not forget their. Yeah. So.
Di lobby mungkin
Yeah.
ya? Atau
You do it.
Sini aja ada poster.
mungkin lampunya nyalain aja. Nah, kelihatan. Ayo, teman-teman. Profesor.
What?
Profesor. Oh iya, bentar diatur. Bentar ya, 2 sesi foto. Good.
You want this one?
No, it's ready. Kelihatan semua? 1,
Saku?
2, 3. Cheese. 1, 2, 3. Gaya bebas, gaya bebas. Sarangnya ya. 1, 2, 3. Last one.
1,
2. Ya.
You're welcome. My pleasure. Yes, thank you very much for attention. So, gerne. So.